I can also say orally happy birthday to you. As it happens, it is also my happy birth date. It's not my birth month. Okay, so first of all, this will be talk. There will be an elementary talk. I have been listening to talks yesterday. They are all very deep and very recent. As you can imagine, mine will be very old. So I'll be talking about it. And then recently I have been discussing with one of my ex-students and trying to do something related to this. At the end, I'll mention that also. So as you can see, even before I switch it off, switch it on, you can read that, I guess. So as you all know, for elliptic curves, every elliptic curve is the intersection of two quadrics in P3. So it came naturally. That goes back, I don't know, about 2 centuries. So, so naturally, when hyper-elliptic curves are defined, so which I'll define just now, one looked for some relationship with quadrics. And as I said, recently I have been looking at it because that was recently, meaning about a year ago. I was looking at this, what I had done out with Narasimhan and others about how much, 60 years ago. 60 years ago, I was looking back at that for the following reason. One of my colleagues and one of my students, they were interested in number theory, although she initially worked in algebraic geometry. So geometry over fields and number fields. And this was related to various conjectures and so on and so forth. And they wanted, in particular, to do something about function fields of hyper-elliptic curves. So it was known for elliptic curves. So first non-trivial thing they wanted to do over hyper-elliptic curves. So they came to me and said that whatever you have done seems to be over only complex numbers. Can you do it over a number field? So because the Weierstrass points are all defined only over C, so can you do it in general? Then, therefore, I looked at it again, and then I could rework it slightly differently so that it will work over any number field. So that is why I went back. But more recently, I am interested actually in the geometry of elliptic curves, hyper-elliptic curves, which I'll explain. As I said, some of the results go back to 60s and 70s, but this is what I explained just now. So let me start. So you start with a two-dimensional vector space, and the P is this is just a notation. And you start with a section of O2G plus 2. I could have said any even, but I write it as 2G plus 2. And this means that it is a polynomial in two variables, homogeneous polynomials in two variables of degree 2G plus 2. So you start with that. And then denote the line bundle of degree G plus 1 on the projected line. There is a, let it as a line bundle, this is a sheaf over G plus 1, and I identified with the line bundles. let L be the line bundle, and whenever you have a line bundle, you have a map from L to L square, taking the vector V over a point to V square in L square. It's actually a two-sheeted covering, because if you are given a vector in L square, then you can take plus or minus V. If that is V squared, you can take a plus or minus V. And therefore, there it's two-sheeted. Except that when V is 0, there is only one choice. Okay, so it is a two-sheeted covering which is ramified on the 0 section of the line bundle. So now suppose you have a section of L square, then you pull back this L to L square thing, and then you get actually a two-sheeted cover which is ramified on the zeros of your section, and therefore you get a two-sheeted covering ramified along the zero section of this section. This is the hyper-elliptic curve. So hyper-elliptic curves are in one-to-one correspondence with 2G plus 2 linear forms, except that you can have a the projective group will identify two of those, will give an isomorphism. Now, if you have a linear form on O2G, it gives a quadratic form on DOG, as I said, that is L and this is L squared, if you like. Therefore, you have a map gamma DOG to gamma DO2G. Over C, the sections of the 2G plus 2 linear form polynomial which I took has xi as its zeros, which is distinct. And therefore, this map, D is only a finite set in that case. So it is like sigma lambda xi squared. Therefore, you have a natural map gamma DOG to gamma DO2G. And if you take a linear form there, you get this is a quadratic map. So together you will get a quadratic form on gamma DO2G. This is a 2G plus 2 dimensional vector space, because D consists of 2G plus 2 points. D is the zeros of that sigma. I haven't written it right, so you don't know what is D. D is the zeros of that. I started with a 2G plus section of 2G plus 2. So sigma has 2G plus 2 zeros, and that divisor is called D. Okay? Is it clear? Now we have a canonical quadratic form on V. V is gamma D OG. Okay? So it is simply a 2G plus 2 dimensional vector space. You have a 2G plus 2 points, and you have a line bundle on 2G plus 2 points. Right? So we can define the canonical quadratic form, God given, because you have a section, you have a map O minus 2 to O2G given by sigma. Sigma is a section of O2G plus 2. Therefore, by tensoring, you have a map from O minus 2 to O2G. And therefore, but you have an exact sequence, O minus 2, O2G, 2G by, this is exactly what I'm saying. So, therefore, we have an exact sequence. The cohomology sequence for this, gamma O minus 2 is 0, gamma O P O2G, gamma D O2G, because it's restricted. And then you have H1 of O minus 2. O minus 2 is the canonical bundle on P1. And therefore, it is H1 of that is C. And then H1 of O2G is 0. So you have the short exact sequence. That exact sequence gives a vector space sequence here. Dually, you can say, you can leave it at that, but you can also do it dually. The dual of C is C, gamma dO2G star, gamma PO2G star. So since you have one here, you have a canonical linear form on O2G. And I have explained to you, if you have a linear form on O2G, you get a canonical quadratic form on the 2G plus 2 vector space V. So as soon as you give any element of gamma O2G star or given a quadratic form, as I said, composed with gamma dO G to gamma O2G and so on. Take gamma G to go to gamma O2G, which is just a squaring map. Simply xi goes to xi squared. X1 try x2G plus 2 goes to x1 squared, x2 squared. You can think of it that way. And thus we give a two-dimensional quadratic diagonal quadrics. Such a quadric, because if there is a two-dimensional space of quadratic forms, we call it a pencil of quadrics. Essentially, if you are given two quadrics, that's enough, two quadratic forms, then you can take the sum of those two. So many people think of it as intersection of two quadrics, or you're given two quadrics and so on. But I like to think of it as a pencil of quadratic forms, which is parameterized by P1. Or you can say a two-dimensional vector space of quadratic forms, or you can say quadrics parameterized by projective line. So as you know, if in projective line has a canonical rational normal curve, therefore every point of P will give you a linear form on PO2G star. And I just now said, I have explained, gamma O2G star will give you a, so will give you a quadratic form or quadratic on gamma POG, right? Maybe I'm repeating. Gamma O2G, OG to gamma PO2G, there is a quadratic form, quadratic map. And then if you take a linear form, by composing, you get a quadratic form on gamma POG. So here, for every P, there is a rational normal curve, that for every P, you have a natural pencil. So, to summarize, what I have done is starting with just a, as I said, homogeneous polynomial in 2G plus 2 degree. I have started with that, and I have thus defined first a vector space V of dimension 2G plus 2. Namely, the basis of this vector space is simply the zeros of that sigma. Okay, there are 2G plus 2 zeros. Take a free vector space over that. That is V. And I defined a God-given quadratic form on this. And then for every P in the projective space, I gave you a pencil which contains this canonical form, canonical quadratic form. This pencil I will call natural pencils because we didn't have to choose anything in order to get this pencil. Now, therefore, we are interested now, why we are interested in quadratic spaces, that is space with a quadratic form, which I explained. Why should a guy who is interested in hyper-ellipticals, why should he worry about quadratic spaces? I have explained that now. if it's a quadratic space of dimension 2G plus 2, then any subspace to which the quadratic form restricts to 0 is called isotropic. So it's a subspace of the Grassmannian, so variety of the Grassmannian, of d-dimensional subspaces of V, consisting of only isotropic subspaces of this quadratic form. That will be empty if D is greater than G plus 2, that is, if the dimension is more than half of the total space, then there is no plane which is contained, no subspace of that dimension which is contained in that. So, and if G is exactly half, then it has two components. As well known, maximal isotropic spaces have two components, and both of them two irreducible varieties. It's a disconnected space consisting of two connected components. Each of these is irreducible. So, for notation, we will occasionally choose one, call it I, and if I occasionally go to the other one, I will call it I prime. No, naturally I is contained in the P lambda G plus 1V because it's contained in the Grassmannian. The Grassmannian is contained in the projective space of lambda G plus 1. Therefore, the induced, you get a line bundle on I, that is maximal isotropic spaces. This is the line bundle. We can say exactly to every V, we can also give it's a determinant dual actually. And this is the square of a line bundle, which is usually called Pfaffian. That is, in other words, maximal isotropic spaces, the variety is contained in the variety of Grassmannian. Therefore, there is a natural line bundle there. You pull it up here, and then it becomes a square of a line bundle, and that is called the Pfaffian. The special orthogonal group acts on all these varieties, ID. Because it is special, it also leaves each component invariant. In any case, that's connected. Therefore, it will leave this I invariant, I and I prime both invariant separately. And it lifts the determinant bundle, because that's why I explained what the line bundle is. So it also acts on that line bundle. You can also check that if you take the Pfaffian and the pullback by any element of SO, Q, it will also be, so it also leaves the Pfaffian invariant. That is, in other words, every special orthogonal element, special orthogonal element group acts on I and takes the Pfaffian to the Pfaffian. Okay, it takes a determinant to the determinant, and because it's connected, it takes the Pfaffian to the Pfaffian. However, the action does not lift, because for each orthogonal you can choose two ways of lifting, and it will not be compatible, and therefore it cannot lift to the Pfaffian. The special orthogonal group does not lift, but if you go to the spin group, the spin group actually lifts. Because over SOQ, there will be two elements in the spin group because the two-sheeted cover, but each of them will leave this invariant, and and the element which acts on the spin group and the quotient is SOQ, then it will take I to I prime. Therefore, you can show that this is a half spin representation. If you take the gamma of, so I'll repeat, if you take the maximal isotropic spaces and take the one of the components, which I called I, and it comes with a Pfaffian line bundle, and the spin group acts on the Pfaffian line bundle. Therefore, it acts on the sections, because if you take SOQ, you will get only a projective representation. This gives actually a linear representation, and and that is the half spin representation. You can identify it with what's called the half spin representation. Now, in fact, I have been talking about the SOQ. These are all algebraic groups and so on. But you can take the finite group, take the special orthogonal group, take the finite group, which is the diagonal group, which is Z2 cross Z2 cross Z2. Okay? And take the inverse image in spin Q, and that is a non-abelian extension of this group. And that also acts on this. And the half spin representation remains irreducible when you restrict to this finite group. This is some kind of a Heisenberg group. So now let me go back to, so suddenly from hyper-elliptic curves, I jumped to orthogonal group. So let me go back to the hyper-elliptic curve. Take line bundles of degree d on the hyper-elliptic curve. I mean, you could have taken any curve, any. In particular, in this case, you will get a Jacobian, which is usually denoted JD. This is a projective variety of dimension G. And this Jacobian often comes with, say, J1, for example, comes with a divisor called the theta divisor. Jg minus 1 comes with, Jg minus 1 comes with a divisor which is called the theta divisor, namely consisting of line bundles which admit a section, non-zero section. Now, instead of theta, if you take r theta and you take the r theta sections of that divisor, it has dimension r to the g. In particular, dimension of 2 theta is 2 to the g. Why do I certainly say this? Because the half spin representation corresponding to SO 2g plus 2, spin 2g plus 2, that is of dimension 2 to the g. That is purely orthogonal. You start with a quadratic form and then you study the Lie groups and representations. Then you get a 2 to the g dimensional vector space. And you take the hyper-elliptic curve and take the Jacobian and take the 2 theta divisors and you try to find the space of sections. That's also 2 to the g. And, and our interest is to explain the similarities between the curve and the orthogonal geometry. And theorem, the variety Ig of isotropic space of dimension G. No, this is, yeah. I'll state the theorem. The variety of isotropic space of dimension G for the whole pencil, it must be isotropic for the whole pencil, that is isomorphic to the Jacobian. So far, I have been talking about only one quadric, but we defined a pencil of quadrics, so you can take isotropic spaces which are contained in both. So if you take the variety of dimension isotropic spaces of dimension G, That is isomorphic to the Jacobian. And similarly for G minus 1, the moduli space vector bundles of rank 2 and with fixed determinant, say delta of odd degree. So should I repeat? I associated to every hyper-elliptic curve of genus G, I associated a 2G plus 2-dimensional vector space and a pencil of quadrics on that. So you take the pencil of quadrics and then do the geometry of quadrics. So take all that Pfaffen and then restrict to that IG, and then you compute the dimension, it's 2 to the G, and it is a Jacobian, the Pfaffian restricts to 2 theta, and it is an isomorphism. So the pair consists of a quadric. You take the quadric of the pencil and a component of the quadric of the pencil and a component of, so the set of quadrics of the pencil is parameterized by P1, right? For a pencil means a 2-dimensional space, so projectively this is a P1. So to every P1, every point of P1, you have a quadric. Now, in the maximal isotropic spaces, that quadric has 2 components. So take one of the components, and so it's a 2-sheeted thing of P1, and that is your curve. Okay. Let S be a subspace of dimensional isotropic for the pencil. We can associate, you can take, for every quadric, you can take S perpendicular, and that will contain S because S is contained in this pencil. S perpendicular over S also comes with a pencil. For each quadric, you get that, and therefore you do it for every pencil, for every point of the pencil. So for every point of P1, you fix a d-dimensional isotropic space for the whole pencil. Now take a point in the point of that pencil, one of the quadrics. You can take S perpendicular over S. Okay, so that's a vector space. And therefore, this way, it essentially gives you a quadratic form. It essentially gives an orthogonal bundle on the curve. Okay, and one can show that this is the association that we have given. We gave for every isotropic space of the we gave a we associated to this to this space. So what I am saying is the following. To sum it up, if there is some confusion, I will explain. Now, we gave, I stated the theorem that the maximal isotropic minus 1 dimension isotropic spaces is isomorphic to the Jacobian, and 2 less is isomorphic to vector bundles of rank 2 with fixed determinant. Now you can ask, if you don't take 1 or 2, if you take any isotropic space of d dimension, for example, does it have any meaning in the curve? So you see, once you have established this relationship between the curve and the quadric geometry, you can go 2 ways. You can take something interesting on the curve and then say, does it have a geometric meaning in terms of quadratic geometry? Or you can do something interesting on the geometry of pencils and then say, does it have an interpretation on the curve? Okay. So this is what I'm saying. So if you take Jacobian is interesting on the curve, I said it is it is some isotropic space for the pencil. Vector bundles of rank 2 is interesting on the curve, and we have an interpretation in terms of maximal in terms of isotropic spaces of certain dimension. Now we can go back. You can say isotropic space of some dimension and then ask whether it has a meaning on the space of the curve. So this is what I did about 50 years ago, try to understand this, and I proved that this is for every point you can give an orthogonal space, and therefore this way you can therefore associate to every maximal to every isotropic space of a fixed dimension an orthogonal bundle on the curve of a special kind, which is actually I invariant, where I is the hyper-elliptic involution for those. So if D equals G or G minus 1, this interpretation is orthogonal bundle of dimension 2 or dimension 4. You can see that actually this is not only an SO bundle, but actually a spin bundle, and then go back to line bundles and vector bundles. Orthogonal bundle of dimension 2 can be lifted, can come from a line bundle, and orthogonal bundle of dimension 4 can be identified with a vector bundle of rank 2. So this way you can generalize in some sense what Narasimhan and I had done earlier. In the 80s, I guess, Hitchin came up with, Nigel came up with what are called, what we used to call Hitchin pairs. And then it somehow nowadays they call it a Higgs bundle, which is a vector bundle together with a section of, it's not IDE tensor K. I'm saying IDE tensor K because I'm assuming the trace, so-called, is 0. And so natural question in this case, so this forms what's called the Higgs moduli on the curve. So you take rank 2 bundles where we have a nice description in the case of curves, in the case of hyper-elliptic curves on. So I repeat, we described the moduli of stable vector bundles of odd determinant in terms of the quadratic geometry. Now there is a new space which is called I would call Hitchin space or a Higgs space, whatever, or Higgs moduli, which is been the subject of many talks here. You take a vector bundle of rank 2, and if you like, a map from E to E tensor K. K is the canonical bundle, and you study. You can define stability for this, and you take the fixed determinant. I will assume odd degree, and then it is a non-singular variety of twice the dimension of the corresponding moduli space of stable vector bundles. Now the question is whether this can also have a description in terms of quadratic geometry. Again, I'll repeat that you have, maybe you can write it down. So you have a vector bundle E, and you have a map. So the pair E phi is called Higgs field. So stability for this, if E is stable, this is stable. But even if E is not stable, sometimes this can be stable. Because stability only requires the degree of line subbundles must be less than something, less than half the degree of E. E is a dimensionally, rank E is 2. So, but for stability for this is you take only line bundles which are L, which go into L tensor K. Only for those you require this degree condition. Therefore, it is possible that E may not be stable, but the Higgs pair, you can admit a Higgs field which is stable. Now, there are immediate remark number one. If E itself is stable, this can be written in terms of the quartic geometry, the corresponding Higgs fields. That space, that open space, is simply the cotangent bundle of the moduli space. I don't know how you write it. This is the vector bundles of rank 2 with fixed determinant delta of odd degree. That is the quota, that I have already described in terms of this pencil. So you have a curve associated pencil. You have a moduli of vector bundles, which is given by isotropic spaces here. Now, if you take Higgs fields, it is a bigger space, so you have a cotangent bundle. Whether now this contains the cotangent bundle of open as an open set, because it's those which are E is stable will be always open, and therefore this will be an open subspace of the Higgs moduli. Higgs moduli. So this is an open subset of that. The cotangent bundle. Now, cotangent bundle, of course, is obviously something which can be defined, which is of interest in the quartic geometry. You take isotropic spaces and take its cotangent bundle. So, but then there are extra points there. So, do they also have some geometric interpretation? That's the question. That's a new thing. But within this table, there are very stable bundles. Very stable bundles are those which admit a phi, which do not admit a phi which is nilpotent. It makes sense to say phi is nilpotent because it's, yeah, in this case we can say simply phi square is 0. Okay? You compose e to e tensor k, e tensor k to e tensor k square, and that should be 0, then it's called nilpotent. So if E does not admit any nilpotent thing, it's called very stable. So now, is there an interpretation of very stable bundles or not very stable bundles, which is a closed subspace in the quartic geometry? Yes, answer is yes. I'll explain to you, easier to explain in genus 2. SUC to delta is simply the intersection of quartics of the pencil. Take all the intersection, you can take two of those and take the intersection. So its intersection of two quadrics is the moduli of vector bundles of rank 2. So now we want a closed subspace which is not very stable. Very stable will be open set, and the complement will be a closed set. So what is the closed set in this? So what are the points in the intersection of two quadrics which correspond to not very stable bundles? That's easy to describe, and that is it's contained in a line. So take a line contained in the intersection of two quadrics. I will now write as Q1 intersection of all the quadrics as a pencil. You take a line. We know lines contained in this correspond to Jacobian, to the Jacobian. I wrote the theorem. So this gives an element of the Jacobian. Okay. Now, you take a line in the pencil which has the following property. L is contained in a plane. Shall I call it L prime P? Is okay. P for plane. L is contained in a plane. This is a line, this is a plane, which is contained in one of the quadrics, any O in the pencil, and whose intersection with the rest of the pencil will be the same, all the other quadrics, because it's 0 on one of them. Therefore, all of them will give you another quadric on this space. I'm saying if you take a isotropic space for one quadric, then the rest of the quadrics will give the same, because they are all linear combinations of Q1 and Q2. And therefore, if Q1 becomes 0, all of them will give the same thing. And that should be a line square. So it is quite strange. Such a line is called a special line. I'll repeat. You take a line in Q1 intersection Q2 with the property that L is contained in a one-dimensional hair, and which is contained in one of the quadrics, and the rest of the quadrics in line square. Okay. So take those lines and take points in that line. These correspond to not very stable bundles. Okay. Now, each L corresponds to a point of the Jacobian. You can ask what is that Jacobian and so on. And this L corresponds to a Jacobian, and then you can write down an extension. And all those extensions corresponding to this element of the Jacobian are all not very stable. Okay. I'm writing, I have decided, I have given certain points of the curve, namely lines in the intersection of two quadrics. And every point of this line will give you a vector bundle. That vector bundle is an extension of this line bundle by psi minus 1 tensor delta. So you take an extension, and those will correspond to points in the line. And if this line is special, then these bundles are not very stable. That is, they give a nilpotent Higgs field. Now, so for example, this is a purely geometric thing, and this gives and And one can easily see that on very stable bundles, if you take a very stable bundle, then the cotangent space on those are trivial up to a finite group. That is, you make a finite ethyl group, and then the bundle, the tangent bundle becomes trivial on those. So you can explicitly write down the isomorphism of this with the product with a three-dimensional vector space. This is three-dimensional in this case. This is three-dimensional. And and this Higgs, yeah, this is six-dimensional. You don't have to say it because cotangent bundle is an open set there. So if this is three-dimensional, this is six-dimensional, but it's six-dimensional. Okay, so that is essentially I am saying up to a finite group, finite extension. This is a trivial bundle over SUC2 delta. SUC delta contains a very stable open set, and on that the cotangent bundle is trivial. We can also give the description in terms of quadratic geometry, what that space is and why is it trivial and so on. And you know that is so. To conclude, you have this space, and the cotangent bundle is an open space in the Higgs space, and there is a open set here on which it's essentially T star is trivial, and that can be described in terms of the quadratic geometry, which I more or less have done. Now, in this case, I said this line corresponds to extensions, but to be precise, I should not say, I should say non-zero extensions up to a scalar, because any extension of this line model by that line model, and if you take the extension and multiply by a non-zero scalar, the vector bundle is going to be the same, isomorphic. And therefore, when I write L, it is not a two-dimensional vector space, but a projective line. When I say L line, it's a projective line. And therefore, if you go to the vector space, you get the vector space extensions. And the point I want to make is, if you take special lines and take the zero vector in the two-dimensional vector space, those correspond to non-stable bundles which allow a stable Higgs. I'll repeat. I have defined special lines purely geometrically. Take special lines, they correspond to two-dimensional vector space, and take the zero of that vector space, and all those correspond to non-stable vector bundles which admit a stable Higgs field. Okay, so so since we have now, and you can also write down explicitly all those Higgs fields. So actually, this will be a two-sheet covering of H naught k square along a divisor. Okay, and you can write down what that divisor is. You can define. They have still not defined the isomorphism of that with the two-sheeted covering. We have given the map, two-sheeted map, but we have not given the covering. So it is ongoing work with one of my students, Sarveshwar Pal, PhD students. And actually in the in this version, I had written down some more detail of this explaining. So I could do the best of what I could do here. I had written the text file completely. This has nothing to do with the project geometry. I had written the text file and then I compiled it, and I was happy because it didn't say there was any problem. So I thought it had compiled it fully. But for some reason, maybe the copying was not good, or what happened, I don't know. But in any case, I have explained, at least to a certain extent, what other geometry I have given. So in other words, finally, many people have been at it over the years. I am not saying that they have been attempting. So Emma Priviato and others have tried to give an interpretation for the whole Higgs array in terms of these quadrics and so on, but it has not been successful. So now I have given a description for the very stable, over the very stable, stable bundles is trivial. On the stable bundles, the corresponding Higgs field is simply the cotangent bundle, which has a good description also in terms of quadric geometry, not just cotangent bundle, but you can describe it as I can describe that. If you take V, usually we call it Y, which is Q1 intersection Q2. And you can take V perpendicular for all the quadrics of the pencil. This is a vector, and they take V perpendicular. And then it's well known that V perpendicular over V, this is a cotangent bundle. Okay, actually see V equals determinant of V perpendicular over V. So this is a three-dimensional space. V is one-dimensional. V perp for one of them is five-dimensional. The other one is five-dimensional. The intersection is four-dimensional. This is four-dimensional. This is one-dimensional, so this is three-dimensional. So you can associate to every point of V a three-dimensional vector space, and the pencil induces one on this. Okay, so we can describe as some three-dimensional subspaces in this space. We have succeeded in doing that. But to extend this, the problem is to extend that to non-stable points. In other words, I'm saying you have very stable bundles, and then bundles which admit Higgs. So there are this range. This and this you can combine. This and this you can combine. But we are now trying to combine all three. So that there will be a description of the Higgs moduli in terms of quadric geometry. Thank you.
Yeah. So there you are describing extensions of two line bundles. Can you say again which are the line bundles that you are? So you said that you are extensions of the two line bundles. This L in the intersection.
Yes, each line corresponds to extensions. Yes.
Which line bundles are you considering?
Which line bundles? roughly speaking, it is slightly different, but essentially this kind of thing. This is of degree 1. So if it is stable, everything will have to be less than half. So you can say in genus 2, you can always there is a degree 0 bundle. So we can write it as I tends to delta minus 1 to, yeah, but then yeah, essentially, I'm not saying it correctly, but the line corresponds to a point in the Jacobian. And, and essentially you get some extension like this.
I think,
You,
aren't you saying that one is, you want to have a nilpotent Higgs field?
pardon?
You're
Yeah.
looking, you want to have a nilpotent.
Yeah, if you take a special line, I think, yeah, something like this. Yeah, wait a minute.
I believe this should be the kernel of the nilpotent Higgs field, which gives you the.
Just 1 minute. Can I say like this? Yeah. I had written that all that in the file, but now I'm struggling. Okay? So it is like this. So, so in other words, it is size h1, psi squared tends to delta minus 1, where psi is of degree 0. So you have this. That projective space of this can be identified with a line. Okay? And if it's a special line, then this will be psi tensor Ox minus 1, O minus x, or some x. If it's a special line, the line is contained in a plane, which is contained in one of the quadrics, and that quadric will give you an element of that quadric, and it's a maximal isotropic space, and therefore it will give you a point of the curve, and that is this x. It's really beautiful that the special line is contained in a plane, which we call special plane, that which is contained in a specific quadric. That plane will be contained in a quadric, and the intersection with the rest of the quadrics will be L square, square of your line. Now it's contained in one quadric, and it's a maximal isotropic space because the dimension is 6 and this is dimension 3. And therefore, it also gives not merely a quadric, but a component of the maximal isotropic spaces, which is exactly a point of the curve. So it gives a point of the curve, and that will be this. I don't know. And from this to K tensor psi, there's a natural map given by x plus ix. You have O minus x to O. So you have a natural map. Psi goes there. O minus x to k, there is a natural map, x plus ix. So there is a nilpotent Higgs. Yeah.
Okay, so
Yeah, just to understand, so just to summarize, what happens. So for each, so we have this cotangent model, and then we have the extra pieces of the Higgs moduli. So for each of them, like there are the components for each of them, we have in a quadratic model. Is that correct? That's I understand.
Yeah, for each.
We have so for which part or in which form do you have this model in this quadratic form, pencil of quadratic forms?
Yeah.
Inside that, what exactly do we have now for these extra components of the Higgs model?
What is the extra?
For these other component, right? So there is the cotangent bundle of the.
You mean non-stable bundles?
Yes, yes.
Which admit, yeah, those are all points in the special line.
Right. So you have.
The special lines
Mhm.
are parameterized essentially by x, but it's actually psi squared is equal to OX or something. So it's a covering 2 to the G covering of the curve. That gives you these special lines.
Yes, I understand.
And any point of the special line, for each special line, which is an extension, you take the zero extension. So each special line gives you a non-stable bundle. That's dimension 1 in this case.
In this case, and
In
so
this case,
for higher
dimension 1.
genus,
You can describe, you
it
can
still
do.
works.
We have more or less done for any genus the same thing. So you can give a description. Now we are concentrating on the genus 2 case. So because we have not still described the whole thing, you know, I said there are 3 things: a space, an open space, and an open space here. There is a description for these 2, namely cotangent model. There is a description for those 2 as a two-sheeted extension of the Jacobian. So we have to, not the Jacobian, two-sheeted extension of H naught k square. Okay? So two-sheeted covering of H naught x k square, which is ramified along a divisor, linear space. So, but all 3 of them, we would like to be, to integrate all of them into one description in terms of geometry. That's what you are doing.
Well, perhaps we should take more questions with the break, because I believe we have a photograph ahead. So let's thank Ramanan for his talk.
So thank you.